In today's lesson, we're going to combine our earlier work with bases with our recent work with orthogonal projections, and we're going to create something called an orthonormal base. If you're not familiar with bases, or if you've forgotten the concept of bases, you're not completely up on it, you may want to go back to your notes and read through a basis before you start this tape. As you move through the series, you're going to find that you forget more and more, and some of the early stuff that I'm just automatically using might be causing a little bit of concern. You really need to develop a practice of reading back through all of your basic notes every couple weeks, so that as I use the terms we developed previously, you'll be ready to understand them and to apply them. Recall that the standard basis for 3-space is 1, 0, 0, 0, 1, 0, 0, 0, 1. The basis has two important characteristics. The first is the vectors are mutually orthogonal, because if we do the dot product of the first two, 1 times 0 plus 0 times 1 plus 0 times 0, we get 0. Do the dot product here, 1 times 0 plus 0 times 0 plus 0 times 1. The dot product here, 0 times 0, 1 times 0, 0 times 1. So no matter which ones you pick, if you do the dot product, you get 0. If the dot product is 0, that means the vectors are orthogonal. The vectors have length of 1. If you go back and calculate the length of any of these, in all cases you'll get it has length of 1. Now the question is, can we make any basis have these two characteristics by doing some type of conversion? Well, we're going to start working on it. A set of vectors in an inner product space V, there should be a capital V, is orthogonal if every pair of vectors in S is orthogonal. So every pair of vectors in the set would be orthogonal to each other. Then we say that the set is orthogonal. If in addition each vector in the set is a unit vector, then S is orthonormal. So orthonormal means all the pairs are orthogonal, all the vectors have length 1. Determine whether B equals to the standard basis for the set of all polynomials of degree 3 or less is orthonormal. Well, first of all, we want to check to see if any pair of vectors would be orthogonal given this definition of inner product. The definition of inner product is PQ is A0 B0 plus A1 B1 plus A2 B2 plus A3 B3. Well, we probably need to write these out so you can see how this definition would follow. On the first one, 1 is the same as 1 plus 0x plus 0x squared plus 0x cubed. X is the same as 0 plus 1x plus 0x squared plus 0x cubed. X squared is the same as 0 plus 0x plus 1x squared plus 0x cubed. X cubed is the same as 0 plus 0x plus 0x squared plus 1x cubed. My inner product is defined to be A0 times B0, so this would be the A0 term. This would be the A1, A2, A3, and so forth, with the general idea that a polynomial P and X in general would be A sub 0 plus A1x plus A sub 2 x squared plus A sub 3 x cubed. So we're assuming this would be a general polynomial within the set. Okay, look at the first two. If I multiply the first two using this, multiply the 0 coefficients together, the 1 coefficients and 2's and so forth, in all cases I'd get 0. If I multiply these, I'd get 0. Multiply, in other words, if you multiply any two of them, you can see that you're going to get 0. So I can say that any pair of dot products is 0. So therefore, orthogonal. Again, if you take these two, 0 times 0 is 0 plus 0 plus 0 plus 0. So in all cases, using this inner product, we'll get 0. Now we need to check for normality. If it's the normal part, which means the norm is 1. Well, that would mean that the norm would be the square root of P with P, using this product, would be 1 for it to be normal. Okay, let's look at P. If we look at this one with itself, that'd be 1 times 1 is 1, plus the rest would be 0. Well, square root of 1 is 1. Here, 0 plus 1, rest are 0. Square root of 1 is 1. 0 plus 0 plus 1 plus 0. Square root of 1 is 1, and so forth. So we can see that it is not only orthogonal, also all the vectors have length 1. The length of P is equal to 1 for all P, an element of the set of polynomials of degree 3 or less. So therefore it is orthonormal. If one has a non-orthogonal basis, then one can use it to construct an orthogonal one. So if you have one that's not, you can use it to construct one that is. So let's consider the plane R2, and let's assume that V1 and V2 form a basis. So we'll draw V1, and I'll come here and draw V2. Now if I come down and do the perpendicular, then this vector, the one I'm shading, is going to be the projection of V2 onto V1. If I call this vector A, I can see that the projection of V2 onto V1 plus A is going to equal to V2. Or I can say A is equal to V2 minus the projection of V1 onto, of V2 onto V1. Now you can see the way I've drawn it, this V2 minus the projection of V2 onto V1 is normal to V1. That's how we drew it. We drew this vector A to be normal to it. But now, what does that equal to? V2 minus, that's the vector A that we're dealing here, V2 minus projection of V2 onto V1 is equal to V2 minus, from the last lesson, V2 dot V1 divided by V1 dot V1 times V1. So we'll let W1 equal V1 and W2 equal to this, V2 minus V2 dot V1 over V1 dot V1 times V1, and we'll get that W1, W2 is an orthogonal basis. The Graham-Smith process extends the concept that we developed for the plane into any vector space. So let's let B equal V1, V2 out to B, Vn be a basis for an inner product space V. So B is any basis for an inner product space V. B prime equal to W sub 1, W sub 2 out to W sub n, where W sub I is given by, so we're going to have to go through and get a lot of stuff here. W1 will always be V1, so W1 will always be the first vector. W2 is going to equal to the second vector minus V2 times minus the inner product of V2 with W1 divided by the inner product of W1, W1 times W1. So now for the plane, this is as far as you go. It is exactly what we did before, but using the general inner product notation. But now we can go all the way out to n vectors. For W3, is going to be V3 minus, now the inner product of V3 with V1 over, with V3 with W1 over W1, W1 times W1, excuse me, minus the inner product of V3 with W2, the inner product of W2 with W2 times W2. Now, this is as far as I took it. I just said dot, dot, dot. But if you go out to Wn, then it's going to be Vn minus Vn with W1 minus Vn with W2 minus Vn with W3 and so forth. In other words, you build it as you go. So the W's will be an orthogonal basis for V. Now once you get it orthogonal, it's very easy to get it to be orthonormal. One can get an orthonormal basis by converting each vector in B prime to a unit vector having the same direction. So that would just be the W1 divided by the magnitude of W1, W2 divided by the magnitude of W2, and so forth. Well, let me illustrate the process with an example. B is equal to the set of ordered triples 0, 1, 2, 2, 0, 0, 1, 1, 1. And B is a basis for R cubed. Now I'm not going to go through and prove it for you, just it is though. Convert B to an orthonormal basis. Well, first of all, let's apply the Graham-Smith process to get an orthonormal base. An orthogonal base. But what we want to do first is let W1 equal V1. In other words, we're trying to get V prime, which would be the W's, and we need to let W1 equal to V1. So the first step would just be let W1 equal to V1, which is 0, 1, 2. Now, W2 is going to equal to V2 minus the inner product of V2 with W1 over the inner product of W1 with W1 times W1. So, W2 is going to equal to the inner product, or it's going to equal to V2 minus the inner product of V2 with W1 over the inner product of W1 with W1 times W1. Well, this is going to equal V2, which is 2, 0, 0, minus. Well, the inner product defined on R3 is just the dot product, so it's going to be V2, which is 2, 0, 0, dot W1, which is 0, 1, 2, over W1, which is 0, 1, 2, dot 0, 1, 2, times, or just a scalar times W1, which is 0, 1, 2. Well, this is going to be 2, 0, 0, minus. Okay, the dot product, 2 times 0, 0, plus 0, plus 0. So this is just going to be 0 over 0 plus 1 plus 4. So that's 1 plus 4 is 5 times 0, 1, 2. Well, 0 times all these would be 0. So that means W2 is just going to be 2, 0, 0. So we kind of had a good example here, but you see the process. It would be the same if this hadn't been 0. You just have to multiply through by the scalar and do the subtraction. So we have W1 and W2. Well, for W3, if you look, that's going to be V3 minus the inner product of V3 with W1 over the inner product of W1 with W1 times W1 minus V3 with W2 over the inner product of W2 with W2 times W sub 2. Well, V3 is going to be 1, 1, 1 minus, okay, the inner product of V3 with W1. Well, V3 is 1, 1, 1 dot W1 is 0, 1, 2 over W1 dot W1. 0, 1, 2 dot 0, 1, 2 times 0, 1, 2 minus V3, which is 1, 1, 1 dot W2, which is 2, 0, 0 over W2 dot W2 times W2, which is 0, which is 2, 2, 0, 0. Now that should just have times there rather than the dot, because you're going to think it's dot product. It's not, it's just the scalar times the vector. Now this is going to be 1, 1, 1 minus, okay, I need to do this dot product, 1 times 0, 0 plus 1 plus 2, so that's going to be 3 over 0 times 0 plus 1 plus 4, it's going to be 5 times 0, 1, 2 minus 2, 0, 0, so that's going to be 2 over 4, 0, 0 times 2, 0, 0. So it's going to be 1, 1, 1 minus 0, 3/5, 6/5 minus 2/4 is 1/2. 1/2 of 2 is 1, 0, 0. Now 1 minus 0 minus 1 is 0. 1 minus 3/5 is 2/5. Minus 0 is 2/5. 1 minus 6/5 is negative 1/5. Minus 0 is negative 1/5. So B prime, which is equal to W1, W2, W3, which is equal to the set W1, if you look back, was 0, 1, 2. W2 was 2, 0, 0. W3 is 0, 2/5, negative 1/5 is an orthogonal basis. But I asked you to convert it to an orthonormal basis. So we need to go through and divide each vector by its magnitude. So to convert it to the normal ones, I'll call it W1 prime, is going to be 0, 1, 2 divided by the magnitude, 0 squared plus 1 plus 4. So that would be 0, 1 over the square root of 5, 2 over the square root of 5. And of course we probably should rationalize, but I'm not. W2 prime would be 2, 0, 0 divided by the magnitude, which would be 4 plus 0 plus 0. Well, that's going to be 1, 0, 0. Because the square root of 4 is 2, 2 divided by 2 is 1. W3 prime is going to be 0, 2/5, and negative 1/5 divided by the square root of 0 plus 4/25 plus 1/25, which is 0, 2/5, and negative 1/5 divided by the square root of 5/25. Which is going to be 0, 2/5, negative 1/5 divided by the square root of 5 over 5. Invert and multiply. It's going to be 0, 2, negative 1 divided by the square root of 5, because when I invert and multiply, I'll be multiplying the top by 5. So that would be 0, 2 over the square root of 5, negative 1 over square root of 5. So my the orthonormal base would be W1 prime, which is 0, 1 over square root of 5, 2 over square root of 5. W2 prime, which is 1, 0, 0. And W3 prime, which is 0, 2 over the square root of 5, negative 1 over the square root of 5.